This chapter discusses NoSQL databases. Let's start with the introduction. We kick off by discussing the NoSQL movement. We then review various types of NoSQL databases, such as key-value stores, tuple and document stores, column-oriented databases, and graph-based databases. The chapter concludes by briefly elaborating on some other NoSQL categories. RDBMSs put a lot of emphasis on keeping data consistent. They require a formal database scheme, and new data or modifications to existing data are not accepted unless they comply with this scheme in terms of data types, referential integrity, etc. Moreover, the way in which they coordinate their transactions guarantees that the entire database is consistent at all times. However, this focus on consistency may become a burden because it induces overhead and hampers scalability and flexibility. As the data volumes or the number of parallel transactions increase, capacity can be increased by vertical scaling or horizontal scaling. Vertical scaling aims at extending storage capacity and/or CPU power of the database server. Horizontal scaling introduces multiple DBMS servers typically arranged in a cluster. RDBMSs are not really good at extensive horizontal scaling. Indeed, their approach towards transaction management and their urge to keep data consistent at all times induces a large coordination overhead as the number of nodes increases. Furthermore, their rigid database schemes make them unsuitable in big data settings, which often include semi-structured or volatile data. Hence, in situations where massive volumes, flexible data structures, scalability, and availability are more important, other types of systems may be called for. This need resulted in the emergence of NoSQL databases. The term NoSQL has become incredibly overloaded throughout the past decade, so that the moniker now relates to a variety of meanings and systems. The modern NoSQL movement describes databases that store and manipulate data in other formats than tabular relations, or in other words, non-relational databases. In that sense, the movement should have more appropriately been called NoRel, especially since some of these non-relational databases actually do provide query language facilities which are close to SQL. Because of such reasons, people have started to change the original meaning of the NoSQL movement to stand for not only SQL or not relational instead of not SQL. NoSQL databases aim at near linear horizontal scalability, which is achieved by distributing data over a cluster of database nodes for the sake of performance as well as availability. A certain measure of data consistency is often sacrificed in return. A term used in this respect is eventual consistency. The data and respective replicas of the same data item will become consistent at some point in time after each transaction, but continuous consistency is not guaranteed. This table provides a more detailed comparison of the typical characteristics of NoSQL databases against those of relational systems. We will zoom into these characteristics into the remainder of this chapter. More specifically, we discuss key value, tuple, document, column, and graph-based databases. A key value-based database stores data as key value pairs. The keys are unique and represent the sole search criterion to retrieve the corresponding value. This approach maps directly to a data structure also present natively in the majority of programming languages, namely that of a hash map or hash table or dictionary, as it is also called. Java provides the hash map class, which allows to store arbitrary objects in internal memory based on a single key. You can see this illustrated here. We create a hash map object, age by name, which keeps track of the age based on the name. We then add 4 entries and illustrate how an entry can be retrieved using the get method. Since keys are unique, the final statement will override the age value for SEPA. To make the data structure of a hash map more efficient, its keys, such as BART, SEPA, and so on in the previous example, are hashed by means of a so-called hash function. A hash function is a function which takes an arbitrary value of arbitrary size and maps it to a key with a fixed size, which is called the hash value, hash code, hash sum, or simply the hash. Each hash can be mapped to a space in computer memory, allowing for rapid, exact lookup of a key. You can see this illustrated here. We use a trivial hash function, which converts keys to a double-digit value. When storing the key value pair, BART 46, the hash value of the key will be calculated as hash BART equals 07. The value 46 will then be stored on address 07. Conversely, when a user wishes to retrieve the value for key BART, the lookup in memory can be performed immediately based on hash BART equals 07. A first key characteristic of NoSQL databases is that they are built with horizontal scalability support in mind and can be easily distributed. The idea is to distribute the hash table over different locations. Expanding our previous example, imagine that our hash table of ages exceeds the limits of our computer's memory. We decide to bring 2 more computers into the mix, over which our hash table must now be distributed. We need to spread our hashes over 3 servers, which can be done easily using the mathematical modulo, or the remainder after division, of each hash. For example, index hash equals modulo hash number of servers plus 1. You can see this illustrated here. For instance, hash 08 divided by 3 has a remainder of 2, which results in index 3 after adding 1. This whole operation can be regarded as another hash function, so that every key, Wilfred, SEPA, and so on, is now hashed to a server identifier, server number 2, server number 1, server number 2, and server number 3. It is worth emphasizing that the concept of hashing can be used to convert keys to locations or addresses within a node or server, and can be used to assign or distribute values over a list of resources, such as multiple servers as illustrated here. This practice of partitioning data and assigning it to different nodes is also known as sharding, and an individual partition is often called a shard. A famous early example of a NoSQL database built on the ideas explained earlier is Memcached. Memcached implements a distributed, memory-driven hash table, or key value store, which is put in front of a traditional database to speed up queries by caching recently accessed objects in RAM. In that sense, Memcache is a caching solution rather than a persistent database. The memcached hash table can grow very large, up to several gigabytes, and can be scaled horizontally across multiple servers in a data center. Memcached has many client libraries in many languages. This example illustrates a trivial Java program using the popular SPY memcached library. We start by creating 3 memcached servers. We then create a memcached client object and connect it to our 3 servers. We use the add method to add 4 entries. Note that the second parameter of the add method indicates the expiration, where the value 0 means no expiry. The set method can be used to set an entry regardless of whether it already exists. You can think of it as an update or insert. The replace method replaces an entry and does nothing if the key does not exist. You can think of it as an update. The delete method can be used to delete an entry, similar to an SQL delete statement. The get method can be used to retrieve entries, as you can see illustrated. In what follows, we further elaborate on key value stores. More specifically, we discussed request coordination, consistent hashing, replication and redundancy, eventual consistency, stabilization, and integrity constraints and querying. In the case of memcached, it is the duty of the client to make sure requests to store and retrieve key value pairs are routed to the desired node, which will store the data. In many NoSQL implementations, such as Cassandra, Google's Big Table, and Amazon's DynamoDB, all nodes implement the same functionality and can all perform the role of request coordinator, which is the party responsible to route requests to the appropriate destination node and relay back the result status of the operation. Since any node can act as a request coordinator, and clients can send requests to any of such nodes, it is necessary that all nodes remain informed at all times of the other nodes in the network. This problem is addressed through a membership protocol. Each node talks to the network to retrieve a membership list and keeps its view of the whole network up to date. This protocol allows all nodes to know about the existence of other nodes and is the fundamental underlying protocol on top of which other functionality can be built. Each membership protocol contains 2 subcomponents called dissemination and failure detection. The basic idea behind this dissemination involves periodic, pairwise communication with the information exchanged in such interaction being bounded. When two nodes interact, the state of the node, in other words, the node's current view on the network, being most out of date, will be updated to reflect the state of the other party. When a node is added to the network, it will contact a known existing node to announce its arrival, which will then be spread throughout the network. When a node is removed from the network, it will not respond anymore when contacted by a random different node. The latter node can then spread this information about this node being down further through the network. In this way, the aspect of failure detection is handled. Thanks to the membership protocol, nodes are eventually aware of one another. They can now partition hashed key value pairs amongst them. To do so, consistent hashing schemes are often used, which avoid having to remap each key to a new node when nodes are added or removed. Suppose we have a situation where 10 keys are distributed over 3 servers, or n equals 3, with the hash function key modulo n. Here you can see what happens when a server is removed, n equals 2, or added, n equals 4 respectively. Note how, upon removal or addition of a server, many items have to be moved to a different server as highlighted in red. Clearly, this is not a desirable outcome in setups where servers are likely to be removed or added. A consistent hashing scheme resolves this issue. At the core of a consistent hashing setup is a so-called ring topology, which is basically a representation of the number range 0 to 1 as illustrated here. In this setup, all 3 servers with identifiers 0, 1, 2 are hashed to place them in a position on this ring, as you can see here. To distribute the keys, we follow a similar mechanism where we first hash each key to a position on the ring and store the actual key value pair on the first server that appears clockwise of the hashed point on the ring. For instance, for key 3, we obtain a position of 0.78, which ends up being stored on server 0. Because of the uniformity property of a good hash function, roughly 1 divided by n of key value pairs will end up being stored on each server. This time, however, most of the key value pairs will remain unaffected if a machine is added or removed. For example, say we add a new server, server 3, to the ring. Only the keys positioned on the blue highlighted section of the ring in the figure would have to be moved to the new server. Typically, the fraction of keys that needs to be moved when using this setup is about k divided by n plus 1, with k the number of keys and n the number of servers. This is a much smaller fraction than was the case for modulo-based hashing. The basic, consistent hashing procedure, as described earlier, is still not ideal. First, if 2 servers end up being mapped close to one another, one of these nodes will end up with few keys to store, as the distance between the 2 nodes on the ring is small. Second, if a server is added to the ring, we see that all of the keys moved to this new node originate from just one other server. Instead of mapping a server S to a single point on our ring, we map it to multiple positions called replicas. For each physical server S, we hence end up with R, the number of replicas, points on the ring, with everything else working like before. By using this mechanism, we increase the uniformity with which key value pairs will end up being distributed to servers and can also ensure that an even lower number of keys must be moved when a server is added to a cluster. Note, however, that this concept has nothing to do with redundancy, since each replica for a node still represents the same physical instance. Many vendors refer to this concept as virtual nodes, as the nodes placed on the ring correspond to a lower number of real physical nodes. To handle data replication or redundancy, many vendors extend the consistent hashing mechanism outlined above, so key value pairs are duplicated across multiple nodes. For instance, by storing the key value pair on 2 or more nodes clockwise from the key's position on the ring. To ensure an even greater amount of data safety, it is also possible to set up a full redundancy scheme, where each node itself corresponds to multiple physical machines, each storing a fully redundant copy of the data. You can see this illustrated here, with server 2 being backupped over 3 hard drives or machines. Recall that the membership protocol does not guarantee that every node is aware of every other node at all times, but guarantees that up-to-date information will spread through the network so it will reach a consistent state over time. This affects read and write operations clients perform, as they must deal with the fact that the state of the network might not be perfectly consistent at any moment in time, though will become eventually consistent at a future point in time. Many NoSQL databases guarantee so-called eventual consistency. Contrary to traditional relational databases which enforce ACID, atomicity, consistency, isolation, and durability on their transactions, most NoSQL databases follow the base principle: basically available, soft state, eventual consistency. The base acronym was originally conceived by Eric Brewer, who is also known for formulating the CAP theorem, which states that a distributed computer system cannot guarantee the following 3 properties simultaneously: consistency, all nodes see the same data simultaneously; availability, which guarantees that every request receives a response indicating a success or failure result; and partition tolerance, which implies that the system continues to work even if nodes go down or are added. Standalone RDBMSs need not bother with partition tolerance, because there's only a single node, so they can focus on consistency and availability. Distributed RDBMSs typically attempt to enforce consistency at all costs in a multi-node setting, which may affect availability if individual nodes cannot be reached. Most NoSQL databases sacrifice the consistency part of CAP in their setup, instead striving for eventual consistency, indicating that the system will become consistent over time once all inputs to that system stop. The full BASE acronym stands for basically available, indicating that NoSQL databases adhere to the availability guarantee of the CAP theorem; soft state, indicating that the system can change over time, even without receiving input, since nodes continue to update each other. Eventual consistency, indicating that the system will become consistent over time, but might not be consistent at a particular moment. The operation which repartitions hashes over nodes if nodes are added or removed is called stabilization, and should preferably be as efficient as possible to reduce network overhead or waiting time. If a consistent hashing scheme is being applied, the number of fluctuations in hash node mappings will be minimized, hence leading to a shorter stabilization period. Key value stores still represent a very diverse gamut of systems. Some systems are full-blown DBMSs, whereas others are merely used as caches in front of a relational DBMS. Typically, only limited query facilities are offered, with an interface that often comes down to simple put and get instructions with the key as the defining single hit parameter. Also, there are limited to no means to enforce structural constraints on the data. The DBMS remains agnostic to the internal structure. Moreover, no relationships, let alone referential integrity constraints or database scheme, can be defined over the respective elements stored in the database. Any constraints or relationships are to be managed and enforced entirely at application level. Therefore, the main feature of key value stores is their ability to offer a very efficient and scalable, yet simple environment for storing and retrieving unrelated data elements. A tuple store is essentially the same thing as a key value store, with the difference that it does not store pairwise combinations of a key and a value, but instead stores a unique key together with a vector of data. An entry in a tuple store could then look as illustrated here for Mark. There is no requirement of each tuple in the tuple store to have the same length or semantic ordering, meaning that the handling of data is completely schemeless. Unlike relational databases, where each table is defined under a particular scheme, tuple stores simply allow you to start adding any sort of rows and leaves the handling and checking of those up to the application. Various NoSQL implementations do, however, permit organizing entries in semantical groups, often called collections or even tables, which is basically an extra namespace defined over the keys. For instance, a collection person might hold two entries, as you can see here. Making the jump from a tuple store to a document-based NoSQL database is easily done. Remember, it's easily done. Rather than storing a tuple-based structure, unlabeled and ordered, document stores store a collection of attributes labeled and unordered, representing items that are semi-structured. For instance, a book can be described using a collection of attributes, as you can see here. Just like with key value or tuple stores, no scheme needs to be defined over the items in a collection. Most modern NoSQL databases represent documents using the JSON standard, which includes numbers, strings, booleans, arrays, objects, and null as its basic types. You can see this illustrated here. In what follows, we further elaborate on tuple and document stores. More specifically, we discuss items with keys, filters and queries, complex queries and aggregation with MapReduce, and the role of SQL. Most NoSQL document stores will allow you to store items in tables or collections in a schemaless manner, but will enforce that a primary key be specified over each table to uniquely identify each item in the collection. This can be done by leaving it up to the end user to indicate which attribute should be used as the unique key, such as with Amazon's DynamoDB, or by predefining an always present primary key attribute itself. MongoDB, for instance, uses _ID as the primary key attribute in an item, which can be set by the user or left out. If left out, MongoDB will auto-generate a unique random identifier for the item. Just as with key value stores, the primary key will be used as a partitioning key to create a hash and determine where the data will be stored. Just as with key value stores, the primary key of each item can be used to rapidly retrieve a particular item from a collection. But since items are composed of multiple attributes, most document stores can retrieve items based on simple filters. Therefore, they typically also offer a richer API than key value stores, with functionality to query and manipulate document content. To illustrate a basic example, the Java code here shows how you can connect to a MongoDB instance, insert some documents, query, and update them. We set up a Mongo client and Mongo database to establish a connection to MongoDB. Next, we use the delete many method to delete all entries in the books collection. This method needs a filter condition, but since we wish to delete all entries, we pass a blank document here. Next, we add some books using the insert many method. Each book is constructed using a static helper method, getBookDocument. The getBookDocument method is shown at the bottom of my slide. It creates a new document with the fields, title, author first, author last, number of pages, and genres. Note that fields of documents can be documents themselves, such as the author field consisting of first name and last name. MongoDB will use a dot to indicate such fields, so that the full identifier of first name becomes author.firstname. After inserting some books, we perform a simple query using the find method and passing a conjunctive and condition containing three clauses. The author last name should equal Van den Broeke. The genres should contain thriller. The AGG filter is used to search through a list in this case. And the number of pages greater than 100. For each document in the result set, we use the update1 method to set the number of pages to a new value. Running our Java code will produce the result you see here. Apart from basic filtering and querying operations, most NoSQL document stores support more complex queries. For example, this Java code shows how you can perform a query which shows the total number of pages across all books grouped by author. The output is again shown in red. Although NoSQL databases are built with scalability and simplicity in mind, running individual queries with many query criteria, sorting operators, or aggregations can still be relatively slow, even when no relational joining is performed. The reason for this is because every filter, such as author.lastname equals Bosons, entails a complete collection or table scan to figure out which documents match the query statements. The primary key defined for every item forms a notable exception, as this key functions as a unique partitioning index, making efficient retrieval of items possible. Most document stores can define a variety of indexes, including unique and non-unique indexes, compound indexes which are composed of multiple attributes, and even specialized indexes such as geospatial indexes, when an attribute represents geospatial coordinates, or text-based indexes when an attribute represents a large text field. Based on the explanation above, you might notice that document stores exhibit many similarities to relational databases, including query, aggregation, and indexing facilities. One notable aspect missing from most document stores, however, is that of relations between tables. To illustrate this concept, say we start from our book example above, but that we get a request to store more information about each author rather than just modeling it as a list of string values per book like we did before. One way to tackle this problem is to just model the concept of an author as a document on its own and continue to store it in an author list per book as you see illustrated here. This concept is referred to by MongoDB and other vendors as embedded documents. The downside of this approach is that it can quickly lead to data duplication and can make it cumbersome to perform an update to an author's information because every book containing that author entry will have to be updated. A second approach is to create two collections, as you can see here. This approach has the downside that most document stores will force you to resolve complex relational queries by hand at the level of your application code. A third approach to perform complex queries and aggregations is to use MapReduce. MapReduce is a well-known programming model made popular by Google and subsequently implemented by Apache Hadoop. It is an open-source software framework for distributed computing and storage of large datasets. A MapReduce pipeline starts from a series of key value pairs, key 1. A MapReduce pipeline starts from a series of key value pairs, K1, V1, and maps each pair to one or more output pairs. Note hence that multiple output entries per input entry can be produced. This operation can easily be run in parallel over the input pairs. Next, the output entries are shuffled and distributed so that all output entries belonging to the same key are assigned to the same worker. In most distributed setups, the workers will correspond to different physical machines. These workers then apply a reduce function to each group of key value pairs having the same key, producing a new list of values per output key. The resulting final outputs are then optionally sorted per key K2 to produce the final outcome. Let's illustrate a MapReduce pipeline using a simple example. Imagine that we would like to get a summed count of pages for books per genre. Assume we are dealing with a large collection of books. Using a MapReduce pipeline, we can tackle this query by first creating a list of input key value pairs corresponding with the records we want to process. This is illustrated in the table above. Each worker will now start working on an input entry and will apply its map operation. Here, the map function is a simple conversion to a genre, number of pages, key value pair, as you can see illustrated. Our workers will hence have produced the 3 output lists shown here, with the keys now corresponding to genres. Next, a working operation will be started per unique key K2, for which its associated list of values will be reduced. For example, education 120, 220 will be reduced to its sum, 340. The final output list hence looks as illustrated above. It can then be sorted based on K2 or V3 to produce the final desired result. Note that, depending on the query, it might require careful thinking to produce the desired result. For example, if we would like to retrieve an average page count per book for each genre, it seems plausible to rewrite our reduce function as shown here. Again, after mapping the input list, our workers will hence have produced the 3 output lists at the bottom with the keys now corresponding to genres. These can now be reduced to the averages shown here. Note that the reduce operation can happen more than once and can already start before all mapping operations have finished. This is especially helpful when the output data is too large to be reduced at once or new data arrives later on. However, note that it is important to ensure that the end results are correct, which may require rewriting the map and reduce functions. As another example, consider the counting of the number of occurrences per word in a document. Here, you can see the corresponding map and reduce functions. Both are relatively straightforward to understand. Let's return to our MongoDB-based Java examples to illustrate the concept of MapReduce in practice. We will implement an aggregation query that returns the average number of pages per genre, but now taking into account that books can have more than one genre associated to them. This code fragment sets up a new MongoDB database for us to use. The setup database method generates a random collection of books. Here you can see the setup database method. It creates 100 books. For every book, the number of pages and genres are randomly generated. The getRandom method returns a list of strings representing the genres. You can see part of the output of our Java program highlighted in red. Let us now construct our aggregation query. If we would perform this query manually, a basic solution would look as shown here. This code loops through all books in the collection, iterates over its genres, and keeps track of all page counts per genre in a hash map structure. The code produces the results highlighted in red. This code will scale badly once we are dealing with millions of books. If the list of genres is known beforehand, we can also optimize this query somewhat by performing the aggregation per genre directly in MongoDB itself, as you can see here. This produces a similar output as you can see illustrated. Assume now that we have millions of books in our database and we do not know the number of genres beforehand. Looping through all books to fetch all possible genres and then constructing a list of averages per genre would be very time consuming. So it makes sense to rewrite our logic using a MapReduce approach. In MongoDB, the map and reduce functions should be supplied using JavaScript code and using the two prototypes shown here. Let's start with building the map function. We need to map each incoming document item to a number of key value pairs. Because we want to create aggregate page counts per genre, our key will be the genre of an item, with its value being a pair composed of the current running average and the number of items used to create the average. The reduce function will then take a list of values and output a new averaged result, as you can see illustrated. We can then implement these JavaScript functions in our Java code example by passing them as plain strings to the MapReduce method, as you can see illustrated here. Running the Java code gives us the same result as before, but now achieved in a MapReduce fashion. Based on the MapReduce example shown above, it becomes clear that many traditional group by style SQL queries are convertible to an equivalent MapReduce pipeline. That is the reason many Hadoop vendors and document store implementations express queries using an SQL interface, most often using a subset of the SQL language, offering users a more familiar way of working rather than requiring them to think in MapReduce logic. Some document stores, such as Couchbase, also allow you to define foreign keys in document structures and to perform join operations directly in queries. This means that the following query is possible using Couchbase N1QL, which is Couchbase's SQL dialect. Select books.title, books.genres, authors.name from books, join authors on keys, books.authorID. The line between RDBMSs and NoSQL databases has become blurred over the years, and we see vendors of relational databases catching up and implementing some of the interesting aspects which made NoSQL databases and document stores especially popular in the first place. These aspects include focusing on horizontal scalability and distributed querying, dropping scheme requirements, support for nested data types or allowing to store JSON directly in tables, support for MapReduce operations, and support for special data types such as geospatial data. This comes backed by a strong querying backend and SQL querying capabilities. A column-oriented DBMS is a database management system that stores data tables as sections of columns of data rather than as rows of data as in most DBMS implementations. Such an approach is useful in applications where aggregates are regularly computed over large numbers of similar data items or when the data is sparse with columns having many null values. Note that being column-oriented rather than row-oriented is a decision that stands quite orthogonal to the type of data being stored. This means that relational databases can be both row and column-oriented, and so can key value or document stores. To illustrate the basic workings of a column-oriented database, Imagine a database system containing the rows you see here. A row-based system is designed to efficiently return data for an entire row, which matches the common use case where users wish to retrieve information about a particular object or entity, such as a book with ID 3. However, such systems are not efficient at performing operations that apply to the entire dataset, as opposed to a particular row. For example, if we want to find all records in our example with a price above 20, we would need to seek through each row to find the matching ones. Most database systems speed up such operations by means of indexes. However, maintaining an index also adds overhead, especially when new data enters the database. In a column-oriented database, all values of a column are placed together on disk, so our example table would be stored as you can see illustrated here. In this way, one particular column matches the structure of a normal index in a row-based system, an iteration of possible values together with the record identifiers holding that value. However, the need for separate indexes disappears here, as the primary keys for each column are the data values themselves, mapping directly to record identifiers. For example, genre fantasy maps to records 1 and 4. Operations such as find all records with price equal to 10 can now be executed directly in a single operation. Other aggregation operations, such as sums, averages, etc., over columns can be split up in this manner as well. Moreover, null values do not take up storage space anymore. Only cells that contain an actual value are present in the storage scheme. There are also disadvantages to this approach. To begin with, retrieving all attributes pertaining to a single entity becomes less efficient. It is also clear that joining operations will be slowed down considerably, because every column must now be scanned to find values belonging to a certain foreign record identifier, rather than being able to immediately retrieve a particular record by its identifier directly. Examples of column-oriented databases are Google Bigtable, Cassandra, HBase, and Parquet. Of all the categories of NoSQL databases, graph-based databases may become the most significant in the future. Graph databases apply graph theory to the storage of information of records. In computer science and maths, graph theory entails the study of graphs, mathematical structures used to model pairwise relations between objects. Graphs consist of nodes, or points or vertices, and edges, or arcs or lines that connect nodes. Arcs can be uni or bidirectional. In recent years, graph structures have become popular due to them being capable to model social networks. For instance, the graph below depicts 3 nodes with edges representing a follows relation, as you would find in a social network, for instance on Twitter or Facebook. The reason why graph databases are an interesting category of NoSQL is because, contrary to the other approaches, they actually go the way of increased relational modeling rather than doing away with relations. That is, one-to-one, one-to-many, and many-to-many structures can easily be modeled in a graph-based way as well. Consider, for instance, books having many authors and vice versa. In an RDBMS, this would be modeled by 3 tables, one for books, one for authors, and one modeling the many-to-many relation. query to return all book titles for books written by a particular author would then look as you can see at the bottom of my slide. In a graph database, this structure would be represented as shown here. The related query to fetch the desired list of books becomes more straightforward, as well as you can see illustrated. Here, we're using the Cypher query language, the graph-based query language introduced by Neo4j, one of the most popular graph databases. We will come back to this in what follows. In a way, a graph database is a hyperrelational database, where join tables are replaced by more interesting and semantically meaningful relationships that can be navigated and/or queried using graph traversal based on graph pattern matching. We will continue to use Neo4j to work out some examples and topics in the following subsections, starting with an overview of Cypher, Neo4j's query language. We also elaborate further on exploring a social graph. Like SQL, Cypher is a declarative text-based query language, containing many similar operations as SQL. However, because it is geared towards expressing patterns found in graph structures, it contains a special match clause to match those patterns using symbols that look like graph symbols as drawn on a whiteboard. Nodes are represented by parentheses, representing a circle. Nodes can be labeled if they need to be referred to elsewhere, and be further filtered by their type using a column as you can see. Edges are drawn as you can see here, representing a unidirectional line or an arrow representing a directional relationship respectively. Relationships can also be filtered by putting square brackets in the middle, as you can see here for the relationship between book and author. Let's look at some examples of Cypher queries. The first query returns all information about books. The second query sorts the books by descending price and returns the first 20. The third query includes a where clause. It returns all information about books whose title is beginning Neo4j. The fourth query adds this condition to the match clause. Join clauses are expressed using direct relational matching. This query returns a list of distinct customer names who purchased a book written by Wilfrid Lemayeux, are older than 30, and paid in cash. Where graph databases really start to shine is in managing tree-based structures. Imagine we have a tree of book genres, and books can be placed under any category level. Performing a query to fetch a list of all books in a category programming and all its subcategories can become problematic in SQL, even with extensions that support recursive queries. Yet, Cypher can express queries over hierarchies and transitive relationships of any depth simply by appending a star after the relationship type and providing optional min-max limits in the match clause. You can see this illustrated in the query at the bottom. All books in a category programming, but also in any possible subcategory, sub-subcategory, and so on, will be retrieved. In this example, we will try to explore a social graph for a book reading club, modeling genres, books, and readers in the structure shown here. We start by inserting some data using Cypher queries, as you can see here. You can do this using the Neo4j web console or using Neo4j's JDBC driver. Note that create statements require you to specify a relation direction, but the actual direction does not matter in this example, as we will query all relations as unidirectional ones. Our complete social graph now looks as depicted here. Let us start now to answer some queries. For instance, who likes romance books? Because there's only one type of relationship between each node type, we can drop the square brackets column selector, as you can see here. The first Cypher query on this slide asks for Bart's friends that liked humor books. The second Cypher query retrieves humor books that Seppa's friends liked and Seppa has not liked yet. A next query asks for a list of people with liked books Bart liked, sorted by most liked books in common. Note that in this query, we are applying an aggregation operator, count. In Cypher, grouping for aggregation is implicit, meaning that as soon as you use an aggregation function, all non-aggregated columns, such as friend.name in our example, will be used as grouping keys. You can see the result of this query highlighted in red. Though graph databases have not become as widely adopted as relational DBMSs by a long shot, it is interesting to note that they have succeeded in various niche application domains. Graph databases are frequently applied in domains such as location-based services, where many topological entities and algorithms can be represented as a graph, such as finding the shortest route amongst two locations. Graph databases are also applied to construct recommender systems in social media. For example, Twitter uses FlogDB to store its social graph, and in knowledge-based systems to provide a semantical representation of resources and rules. Besides key value stores, tuple and document stores, column-oriented databases, and graph-based databases, several other niche NoSQL databases exist. In many cases, these are geared specifically towards storing and querying specialized types of data or structures. Two of these, XML and object-oriented databases, were already discussed before. Other examples are database systems to deal with time series and streaming events, database systems to store and query geospatial data, and database systems such as BaseDB, which let users query the probable implication of their data. Most NoSQL implementations have yet to prove their true worth in the field. Most implementations sacrifice asset concerns in favor of being eventually consistent, and the lack of relational support makes expressing some queries or aggregations particularly difficult, with MapReduce interfaces being offered as a possible, but harder to learn and use alternative. Some early adopters of NoSQL were confronted with some sour lessons. Examples are Twitter, which ended up sticking to a MySQL cluster, or the fiasco of healthcare.gov, where the IT team also went with a badly suited NoSQL database. We see many NoSQL vendors focusing again on robustness and durability. We also observe traditional RDBMS vendors implementing features that let you build scheme-free, scalable data stores inside a traditional RDBMS capable to store nested, semi-structured documents, as this seems to remain the true selling point of most NoSQL databases, especially those in the document store category. Some vendors have already adopted NewSQL as a new term to describe modern relational database management systems that aim to blend the scalable performance and flexibility of NoSQL systems with the robustness guarantees of a traditional DBMS. Here you can see the main differences between RDBMSs, NoSQL databases, and NewSQL summarized once more. We hereby conclude this chapter. We started elaborating on the NoSQL movement. We then discussed various types of NoSQL databases, such as key value stores, tuple and document stores, column-oriented databases, and graph-based databases. We concluded by reviewing some other niche NoSQL databases.